Today I want to talk a little bit more about exponentiating. So this is something that we saw in the proof of Serre's theorem. That was the first time we came across this idea. But actually it's a basic principle. So I want to kind of talk a little bit about it in some generality to start with. So let's maybe let x from v to v, let's say v is a finite dimensional vector space. And I'm only going to talk about this when x is a nilpotent linear map. So given such an x, then you can think about exp of x. So x, just if you want to think of x as a matrix, this is just exponentiating that matrix. 1 plus x squared, that means x composed with x over 2 factorial, and so on. That makes sense as a linear map from v to v. It makes sense as actually this is a finite sum, because all sufficiently large powers of x from some point on are simply 0. I mean, you could if you were over, I don't know, R or C, for example, somewhere where you can make sense of convergent infinite series, you don't need the nilpotency, of course. You can talk about convergence and everything's fine. But hey, we're algebraists, so let's not deal with infinite sums. Let's assume everything is nilpotent. So let me see, what else? If you have another nilpotent linear map, and let's suppose that x and y commute, well then x of x composed with x of y is of course x of x plus y. That's just immediate from just the formal property of the exponential power series, which you could prove. I don't know. You could prove it. You could prove it if you do some analysis. That's just laws of exponents. And so if you actually think about that as being the exponential functions Taylor series, then that's just immediate from laws of exponents. But if you want to if you just wanted to work formally with the power series, you could just prove that directly. It's a little exercise in using the binomial theorem exercise. So if you never did that exercise when you were young and learning calculus, it's worth having a go. So let's see. So that implies in particular that actually exp of x is invertible, because the inverse is just exp of minus x. I've written GLV there, but you know what? I could have written SLV. It's an element of the special linear group because, in fact, it's what's called a unipotent linear map. All its eigenvalues are 1. So you can pick a basis for a unipotent map. You can pick a basis so that the map looks like 1s on the diagonal, ends up a triangular. This is a unipotent linear transformation. So certainly it's got determinant 1, it's in SL of V. Okay, so that's all sort of easy stuff. Let's kind of have a few variations. If V is an algebra, let's call it A instead maybe, and x from A to A is a derivation of that algebra, well then, when you exponentiate x, this is actually an algebra automorphism. That's the next little observation about exponentiating. So let's just, I'm not going to write out the proof, but it's kind of an easy little game. You should write it out in general, but let's just look at the beginning of the exponential series and apply it to a product, A times B, in that algebra. So I've got to apply 1, that's the identity map to AB. Then I've got to apply x to AB, but that's a derivation, so that's x of AB plus ax of B. Then I've got to apply x squared over 2 factorial, but by what are we using? We're using the second order product rule, the second order version of Leibniz. That's doing x squared over 2 factorial to A times B, and then it's doing x to A and x to B, and then it's doing x squared over 2 factorial to B, and I've got the order wrong, and I've run out of space too. And so on, which is exactly A plus x of A plus x squared over 2 factorial of A times, in the algebra, B plus x of B plus x squared over 2 factorial B. So if I just multiply this out, look, there's the AB, there's the x of AB and the ax of B, and then you get the x squared B, the xx, and the ax squared B, and so on, and you can just make sense of that in general. That's essentially the proof. Next, let's think about an element. Let's take a linear Lie algebra. So a subalgebra of GLV. So V here is finite dimensional, and let's take some elements x and y in G, where x is nilpotent. So nilpotency of x, of course, implies that add x is nilpotent too. And what I want to think about is what happens if you take y. So because x is nilpotent, you've got xx, that automorphism. What happens when you conjugate y by xx? Okay, so this right here, I'm using just matrix multiplication. So everything here is an endomorphism of V. Y is an endomorphism of V. This is an automorphism of V. So that's just a composition, if you prefer to say it that way. So the next formula of importance is that xx, y, xx inverse, that conjugate, is the same as taking add x, that's nilpotent, so you can exponentiate that. That gives you an element of the general linear group GL of G, and you can then apply that to y. Okay, so that's an important formula. Let's see where that comes from. It's kind of an easy proof, actually, because you see add x. This is the usual argument that we've used many times, right? When we prove that add x is nilpotent in this case, what do? You write add x as left multiplication by the matrix x minus right multiplication by the matrix x. And those guys commute. And they're both nilpotent. So by the previous page, exp add x is gotten by exponentiating lambda x and exponentiating minus rho x, which is rho x inverse. And so when you apply both sides to y, of course, this just gives you that conjugation. Okay, so that's the proof of my formula. Cool. So actually, the right way to think about this formula is, this conjugation here, right? This is this is an element of the general linear group GL of G, acting on an element of its Lie algebra, GL of V there. And if you remember this conjugation action, that was just the adjoint action of the general linear group on its Lie algebra. So what this left-hand side is, I should really write this as, let me see, where shall I write it here? I should write it as add of exp x. So it's that applied to y. So a better way of writing that formula maybe is that add of exp x is equal to exp of add x. So now let me see. This right here, by the previous fact, this is an automorphism of the Lie algebra G. In fact, automorphisms of that form gotten by exponentiating they're called inner automorphisms. So this is an inner automorphism, which is actually a normal subgroup of the algebraic group of all Lie algebra automorphisms in there. So this sort of exponentiating nilpotent element, these guys, they're inner automorphisms. And right away here now you're starting to see the connection between exponentiating here and algebraic groups. So I want to just do, I think I'm going to do 4 examples. So the easiest example we should start with is SL2. And so I've got my usual SL2 triple EHF. So let's try and exponentiate. So let's just take E and F. And let's exponentiate them in the natural representation, because they're nilpotent, right? So this is pretty easy. So if I'm exponentiating E, so that's going to be the identity matrix plus E, and then it's plus E squared over 2 factorial, but E squared is already 0, so we're done exponentiating E. Actually, it gets a little bit more interesting. I'm gonna exponentiate TE and TF for any complex number T. To exp TE, the only thing that will change is that 1 will become a T, and so you get that matrix. Now let's call this something. Let's call this x of t. So that's an element of SL2 of C, right? It's a unipotent matrix. And of course, by property of by the laws of exponents, x of t prime is x of t plus t prime. This shows that x is mapped from the additive group to SL2 of C, sending just t to x of t. This is a morphism of algebraic groups. Okay, so this is the fact that it's a group homomorphism, and it's obvious that the map sending T to this matrix, I mean, all entries of this matrix are polynomials rather, degenerate polynomials, so it's a morphism of varieties. So this X is a morphism of algebraic groups here. Similarly, we could look at exp of TF, and this is the matrix 1, 1, 0, T. So if I call this thing Y of T in SL2 of C, then we get this Y from GA to SL2 of C, sending T to that matrix. That's also a morphism of algebraic groups. So X is and Y is as well. So these X's and Y's, the image of X, the image of Y, these are often called one parameter subgroups or root groups. So the images of X and Y. Okay, and so now I'm going to observe that these two root groups, X and Y here, actually generate the whole group SL2 of C. It's generated by all X of T and Y of T for T in C. So just by exponentiating these very simple nilpotent elements of the Lie algebra SL2 coming from our favorite generators, you actually get enough automorphisms, enough elements of the group SL2 of C to generate that algebraic group. So let me maybe explain that. Actually, it's kind of useful to, before I explain that, to recall a little fact, which was, I think it was homework 1, question 2. Okay, so we're finally back to homework 1. That's kind of miraculous. And so let me state the result that was proved in that homework problem. It was given a family of morphisms of algebraic groups. The subgroup generated by their images is closed and connected. Hence, it's an algebraic group. In its own right. Okay, so I think I just put the additive group here because that's what I need it for, but this could be any connected algebraic groups there. So this, we're in that situation here, right? Because I'm looking on the right-hand side, I've got the subgroup generated by the images of these X's and Y's, these two root subgroups. So this guy here, it's definitely a closed connected subgroup of SL2 of C. So all I have to actually do, just because it's closed, all I have to do to see the equality here is convince you that this is three-dimensional. And what have we got? Well, we've got the X of T's. That's clearly giving us 1 dimension's worth of subgroup, and the F's gives us an independent 1 dimension's worth of subgroup. So what I need is one more dimension of subgroup here, and I'm going to show you how to get some diagonal stuff in there. So now you actually have to do some matrix multiplying to see this 3 dimensions. We've got 2 of them already. We need 1 more. So here's what I'm going to do. I'm going to take a complex number. In fact, I want a non-zero complex number here. And I'm going to let sigma of t be this crazy matrix product, x of t, y of minus t inverse x of t. So these are really important formulas. Let me just work it out. What is this guy? What is it? It's... So x of t was that matrix. y of minus t inverse is that matrix, x of t. Okay, then you've got to just multiply. So let me see, I'm going to multiply the first two matrices. I get 0 t minus t inverse 1, and then multiply again, 0 t minus t inverse 0. Right, so this guy here, this is the thing I'm calling sigma of t. It's an element of SL2, the group SL2 of C. It's actually an important formula, so let's put a box around that formula. And I'll write simply sigma for sigma of 1. That's also a useful element to have in the group SL2. So this is the matrix just 0, 1, minus 1, 0. Okay, and then the final kind of magic formula here is I'm going to define gamma of t to be sigma of t, sigma of minus 1. So let's work out what matrix that is. So sigma of t, that's this guy. Sigma of minus 1. And so that matrix product gives you, what does it give? T, 0, 0, T inverse in the group SL2 of C. So actually what we've got here is we've got gamma. This is another one parameter subgroup of the group SL2 of C. So this is another morphism of algebraic groups. Just taking T to the matrix gamma of T, that's obviously a homomorphism from the multiplicative group into SL2 of C. So this gives us a one parameter subgroup, which I'll usually denote by T. So that's the set of all these gamma of T's, T being a non-zero complex number, and this is of course a one-dimensional torus. That's our kind of diagonal determinant 1 matrices inside SL2 of C. Okay, so I could have got these by exponentiating the algebra element H, but I prefer to get them by exponentiating these nilpotent matrices and then performing these kind of rather cunning constructions. Once you've got x of t and y of t, constructing gamma of t here. These are the diagonal part. And of course, the Lie algebra of this one-dimensional torus, well, that's our usual torus, the span of H inside our Lie algebra. I guess we can also take, if we went back here, where we've got these x of t's, that's this root subgroup x, and that's another root subgroup y. The Lie algebra of x, that's the span of E in our Lie algebra, and the Lie algebra of y, that's the span of F in our Lie algebra. Great. Okay, so that's the next example. So we can actually kind of think about the adjoint representation. So I'm going to think about SL2 of C in the adjoint representation. So let me first actually calculate the matrices. So I'm going to again think about TE, but in the adjoint representation, and TF in the adjoint representation. Okay, so before I just didn't have anything there, and I was doing the natural representation. Now I'm doing the adjoint representation. So let's just calculate just one more time to see these matrices. So what matrix is this? So this is going to be inside the group GL of G, right? So what we need to know what add E is, And of course, we're using the basis EHF here. So add E sends E to 0, it sends H to minus 2E, and it sends EF is H, right? So that's add E. Oh, I want add TE, so I better stick T's in there. Now I'm exponentiating this 3 by 3 matrix to get the corresponding automorphism of the Lie algebra G. So it's 1 plus TE and then I've got to do what, a half add TE squared. So I've now got to square this matrix, and unlike before, now we do get this squared term in the exponential series, and when you square this matrix, I think you get minus 2t squared up in that corner, and then I've got to divide by 2 factorial, so you get minus t squared. Okay, so this time exponentiating this matrix, it gives us, I need the quadratic term of the exponential series too. I think if you calculate exp add f in a similar way, so add tf is this matrix, fh is 2tf, fe is minus h. So this, when you exponentiate add tf, you get 1 plus add tf, and then I've got to square that over 2 factorial, and that gives me minus t squared. Okay, so these are what you get if you exponentiate in the adjoint representation. But by the one of the facts, I think the third fact that I gave you just before Baker-Campbell-Hausdorff, this is the same as doing add of exp te. And this is the same, which is the thing we calculated. That was our x of t, right? And this is add y of t. Let's find a few more. Let's work out add sigma of t. So I guess I could do this by multiplying 3 such matrices together, but how about we just conjugate directly? So I'm after this 3 by 3 matrix in GL of G. I'm going to take the matrix for sigma of t that we calculated earlier, 0t minus t inverse 0, and I'm trying to conjugate by this matrix. So the inverse is minus t inverse 0, right? And I'm just computing on the basis EHF. Let me maybe just show you the calculation on H. So I've got to plug the matrix H in there, and I've got to conjugate. I think this might be my last matrix multiplication that I can bear to do. So let me see, I'm multiplying the first 2 matrices, 0 minus t inverse 0, and then I've got to multiply one more time. So that's minus 1, 0, 0, 1. Oh, so that's minus h, so that gives me this middle column. H goes to minus h. And I think if in a similar way you calculate the other columns, you find that E goes to minus t to the minus 2f, and f goes to minus t squared e. I might have calculated that correctly. Okay, let's get rid of that calculation. You don't need to see that matrix product. In particular, add sigma. Remember, sigma is just sigma of 1, is this matrix. Sends h to minus h. So this is just like the simple reflection in the Weil group that sends, we're doing SL2, so this is just one-dimensional Euclidean space. The simple reflection is just minus 1. This is add sigma. I'm writing here GL of G, but of course what I'm really doing is I'm calculating the images of these elements of the group SL2 under the adjoint representation. So I'm really calculating elements in add SL2, which is PSL2. So So these are really these matrices in the group PSL2 of C. We're calculating the adjoint representation of the group SL2 of C. Let's do add h of t. So remember, h of t is not, I didn't call it h, I called it gamma. Gamma of t. So gamma of t was sigma of t, sigma of -1. So I've got to take this matrix and I've got to take sigma of -1, and I've got to multiply these matrices, and what do you get? You get t squared 0, 0, 0, 1, 0, 0, 0, t to the -2. So that's what gamma of t is in PSL2 of C, right? So this gamma, this one parameter subgroup, that was my one-dimensional torus T. This is the image of that one-dimensional torus in the group PSL2. And it's worth pointing out that, let me see, add gamma of T on E is T squared E. This was in this add of my one-dimensional torus, whereas we had HE before, right? This H was in our Lie algebra, little t. So I guess maybe I should write it like this, add H on E. That was 2E, right? That was our SL2 relations. And so this is the algebraic group, the one-dimensional torus. It's acting by multiplication by t squared, whereas the corresponding element h in the Lie algebra is acting by multiplication by 2. So this is the multiplicative formula for the torus action. This is the additive formula, t squared or 2. Those are these characters. Moving on, let's do now an important example. We're kind of ready for this now. So now I'm going to take a Cartan matrix C, like we were doing when we were talking about Serre's theorem. So I'm going to take the Lie algebra G of C given by the Serre presentation. And I'm going to look at that SL2 spanned by EI, HI, FI for some I in the index set. Again, and when we were proving Serre's theorem, I looked at this thing I called sigma of I, which was exp add EI, exp add minus FI, exp add EI. This should now look not quite such a remarkable formula. And so this is an automorphism of this G. So this is the step that I skipped when I was proving Serre's theorem. At that point, actually, this G, we didn't know it was a finite dimensional Lie algebra even in that case. But nevertheless, everything we're doing makes perfect sense because we did know that EI and FI were locally nilpotent on G, even if perhaps G was an infinite dimensional vector space. So it still makes sense, everything we were doing back in that proof of Serre's theorem. And we needed to know that on HI, I needed to know that sigma I of HI is minus HI. Well, that's just the calculation that we just exactly made right here. It's exactly the same calculation, and so that establishes that on HI, it sends HI to minus I, and on, let me see, I want to write the kernel of alpha I, so this is sitting inside our T. Remember the T, the maximal torus, the maximal toral subalgebra in the proof of Serre's theorem. It was spanned by the element, the H's in the generators. That was this L-dimensional guy. So this is this codimension 1 subspace. On the kernel of alpha I, well, it's rather easy to work out what sigma I is. It's the identity, because on an element of the kernel, it commutes with EI, right? So add EI is just 0. So you're just exponentiating 0. So that all of these guys are just 1, right? Sigma I is the identity. Okay, so this sigma I acts on T so that it sends HI to minus HI, and it fixes the kernel of the root alpha I. So this means that sigma I on some H in T, let me see, let me put a lambda. It's exactly the same as SI of lambda of H for all lambda in T star. So I'm just finishing up the proof of Serre's theorem. I guess I might want to put an inverse here. I mean, it's sigma I is an involution, so but I'm going to put an inverse there. And this implies that sigma I of G lambda is G SI of lambda. Remember, SI of lambda, this was coming from the root system that we had right at the beginning. This was lambda minus lambda alpha I check alpha I. That was our simple reflection. And you see the simple reflection, it sends alpha I to minus alpha I, and it fixes the hyperplane orthogonal to alpha I, right? Because it's reflection in that hyperplane. So that's where that equation comes from. And from that, you deduce this was the fact that I needed in the proof of Serre's theorem, that these simple reflections permute these weight spaces around in the same way as the simple reflection SI in the Weyl group. That was kind of the key step in proving Serre's theorem. So let me see if I can finish that up finally. So, I mean, what have you got to do? You've got to take an X in G lambda. You've got to look at sigma I of X, and you've got to think how some element of the maximal toral subalgebra T acts on that via the adjoint action. But that's going to be the same as sigma I of sigma I inverse of HX, because sigma I is a Lie algebra automorphism. We've seen that today. And that's, so now X was in the lambda weight space, so that's going to be lambda of sigma I inverse of H on X. I'm applying sigma I of X, right? But we've just seen that lambda sigma I inverse is SI of lambda of H on sigma I of X. And so right there, that's showing that this element here, the way add H acts on it, it's via the weight SI of lambda of H. So that's exactly saying that it's in there. So, sorry, this argument kind of is the step missing in the proof of Serre in lecture 9.3. Okay, so you see this exponentiating now. Hopefully we've done enough of it that this actually seems something rather natural and not a big surprise. Let me do one last thing today. This is all about exponentiating. So still G is G of C. So now we know this is a finite dimensional semi-simple Lie algebra whose type is the Cartan matrix C. Let's let V be any finite dimensional G module. So that means we've got a representation, right? Rho from G to GL of V. And so if you use rho, you can really think about, you can replace G by its image under rho and think of it as being a linear Lie algebra. and apply the stuff we've been doing. In other words, you exponentiate in the representation row. So then you can define, for example, sigma I by exponentiating row of EI, row of minus Fi, row of EI. So this is our same formula that we've been using for these reflections, but now this will be the ith simple reflection, and the arguments above basically show in just the same way that if you take the lambda weight space of V, it takes you to the Si of lambda weight space, where this is the ith simple reflection in the Weyl group, and it implies that the dimension of the lambda weight space of a finite dimensional irreducible representation is equal to the dimension of the W lambda weight space for all W in W, so that the weight space dimensions are constant on W orbits. So last time I was talking just a little bit about the representation theory of these semi-simple Lie algebras, the finite dimensional representation theory, and this is kind of crucial fact. In fact, this comes into the proof of the classification of finite dimensional irreducible representations, and it's essential in the Weyl character formula and the Weyl dimension formula, and so on. So it's the same idea of exponentiating is very important.